Okay, this is going to be our third video on electrochemistry, and here I'm going to talk about voltaic cells. So what is a voltaic cell? A voltaic cell is where we use a spontaneous oxidation reduction, or redox reaction for short, to produce electricity, also called a galvanic cell, basically also called a battery. Okay, what is a battery? How does a battery generate electricity? A battery is a harnessed oxidation and reduction reaction. Because remember that the definition of an oxidation reduction reaction is that it involves the transfer of electrons from one chemical species to another. And what is a battery, or what is electricity? It's a flow of electrons. So what we've done in a battery is force the transfer of electrons to take place through our external circuit. So it's a harnessed redox reaction. So as an example of a spontaneous reaction, let's talk about the reaction between zinc metal and copper sulfate solution. Okay, so we're going to have something like this. So we're going to have some copper-containing solution. Alright, and we're going to add a zinc strip to that. Okay, and so what's going to happen is that the zinc is going to be oxidized to zinc 2. In other words, the zinc solid in the metal is going to oxidize and go to zinc 2 ion in solution, right? That's the definition of oxidation. That's loss of electrons. And then the copper ion in solution is going to pick up those electrons and get reduced down to copper metal. So zinc is itself kind of silvery like aluminum. So if you pull the zinc strip out, after a while you're going to see that it's become coated with the copper metal. And you're familiar with the appearance of copper. It's kind of reddish in color. If you pull the zinc strip out, it would be coated with copper metal. Because the copper, one more time, the copper is going to pick up those electrons and get reduced down to copper metal. So this reaction is spontaneous. If the copper solution is concentrated enough, it can get going pretty good, and the zinc strip can become warm to the touch. But no work is done, because this is basically this is the chemical equivalent here of taking a battery and just shorting it out. So how could we harness this, and how could we make this reaction into a battery? What you have to do is you divide the cell, you divide this into two compartments. We separate this out. Instead of one beaker, we have two. Right? So we have a zinc electrode in a zinc sulfate solution. And again, it doesn't have to be the sulfate. It could be the chloride, it could be the nitrate, whichever. And a copper electrode in a copper sulfate solution. Okay? And we join the two beakers by a salt bridge, which is a U-shaped tube with porous plugs at both ends, and it's filled with an electrolyte solution. Electrolyte solution is one that conducts electricity, such as potassium chloride. Now, the purpose of the salt bridge, I'm going to talk about more about this in a minute, is that it allows sulfate ions, the counter ions, to migrate from one compartment to the other. Okay, so let's diagram this out. So we're going to have two. Now we're going to have, instead of one compartment, we're going to have two. All right, so we're going to have something like this. All right, so we're going to have a solution containing some zinc-containing ion with a zinc electrode. All right, and we're going to have some copper-containing solution with a copper electrode. piece of copper. I say copper electrode, zinc electrode, really just a piece of copper metal and a piece of zinc metal, right? And we're going to join these by this salt bridge. With, like I say, it's a glass tube, U-shaped tube, fitted with porous plugs at both ends. Okay? And that's our salt bridge. Now, when we connect these two to some external circuit, okay, like a light bulb, for example, or a light bulb would light. We've essentially taken this reaction and made it into a battery. All right, so electrons travel. Remember, oxidation has taken place at the zinc electrode. Okay, the zinc electrode is the site, is the anode. That's our site of oxidation. And the copper electrode is the cathode, the site of reduction, right? So electrodes are given off at the zinc electrode. So electrons travel from the zinc electrode to copper electrode. So back to our picture, we have oxidation taking place here. The zinc metal in the strip is oxidizing. Right, and giving up those electrons, okay? And what are those electrons doing? They're leaving the zinc electrode, okay, and traveling through the wire that connects the two electrodes through our external circuit, basically through the light bulb, and then back in to the copper electrode where they pick up, where they're picked up by the copper ion and then used to reduce the copper ion down to copper metal. Okay. So why do we need the salt bridge? Okay. Because think about it. As this reaction happens, as the zinc gets oxidized to zinc 2, there's going to be a buildup of positive charge here because the electrons are leaving. Okay, the electrons are leaving. So there's going to be a buildup of positive charge in that compartment. So this is balanced by the migration of sulfate ions through the salt bridge and into the other compartments. So the sulfate ions migrate from this beaker to this beaker to keep the charge balanced. Okay, and that way the charges stay neutral here and they stay neutral here, right? So electrons flow from the zinc beaker to the copper beaker, and then the sulfate ions flow in the opposite direction. So one more time then, the zinc electrode is the anode, right? That's the definition of anode. That's your site of oxidation. And the copper electrode is the cathode. That's the site of reduction. So electrons travel from the zinc to the copper, all right? And then the sulfate ions travel in the opposite direction from the copper to the zinc. So there's an abbreviated notation that we can use to represent electrochemical cells like this, okay? And ultimately it's going to look, the cell that we just made is going to look like this. But you always write, first of all, you always write the anode cell first. So the oxidation reaction goes first. You write the electrode material and then the electrolyte. And then you write the cathode second with the electrolyte first and the electrode material second. Okay? So a single line represents a phase boundary within one compartment. Okay, such as the boundary between zinc and zinc 2. Okay, so that single line represents a boundary between the zinc electrode material, the zinc metal, and then the zinc ion in solution. Okay, that's a phase boundary. And then a double line represents the physical boundaries, such as the salt bridge. So anode first, electrode material, electrolyte, then the cathode cell with the electrolyte first, electrode material second. Single line is a phase boundary, and then a double line represents the salt bridge. So what we're saying with the way we've written this is we have zinc being oxidized to zinc 2 ion, zinc solid being oxidized to zinc 2, copper 2 being reduced to copper metal. So cell potentials, or the voltage, if you will, indicates the tendency for a reaction to occur. Okay, so with cell potentials, the more positive the number, the greater the tendency to occur. Right? So the more positive the number, the greater the tendency to occur. And this is measured in volts, right? And you have at least some practical experience with this. I mean, everybody's worked at some point with a, let's say, a 9-volt battery. What does voltage really mean? It's the electrical potential, the tendency for the reaction to occur. Now, potential very much depends upon a number of things, including concentration. So you will see in your book, you'll see listings, and some table in the back, you will find listings of electrical potentials. But because potentials depend upon numerous things, you're going to have to specify the conditions, right? So the potentials that you look up are standard cell potentials. Anytime you see that superscript, that means standard conditions, are your potential measured under specific conditions. Okay, so those conditions are a temperature of 298 Kelvin, all components in their standard state. That means for solution, it's 1 molar concentration, and for gases, it's 1 atmosphere pressure. And last condition is that the voltage must be measured when there's no current flowing. Okay, so 298 Kelvin, temperature's 298 Kelvin. Solutions have to have a 1 molar concentration. Gases have 1 atmosphere of pressure and no current flowing. Now, reversing a reaction changes the sign of the potential. Now, this is not a new idea. This is something that we've seen over and over and over again in chemistry too, that often reactions are reversible, and when you reverse the reaction, you change the sign. So for example, when we talked about phase changes, we said the same thing. For example, if you have solid to liquid or liquid to gas, let's say, solid to liquid or liquid back to solid again, the magnitude of the change is the same, but the sign changes. One way is energy in, another way is energy out. Okay, that's the same thing here. You reverse a reaction, you change the sign. Okay, so basically what that means is if you know one, you can calculate the other. If you know the potential for the oxidation, let's say, just reverse the reaction and change the sign, and you'll have a potential for the reduction. So it makes no sense to tabulate both oxidation reactions and reduction reactions. Okay, so that somebody along the way made an executive decision that said we're only going to talk about reductions. We're only going to tabulate reductions, and it's assumed that if you want to know the oxidation reaction, you can reverse the reaction and change the sign. So to obtain the oxidation, reverse the reaction, and change the sign. So if you look up tabulated values, for example, for the reduction of silver, so silver ion being reduced down to silver metal has a positive potential. That's positive 0.80 volts. And remember that then a positive potential indicates a favorable reaction, right? So this is favorable. But if we reverse the reaction, for the oxidation of silver, we change the sign so it becomes negative, and that's equally unfavorable. Okay? Now, if we look at zinc, okay, another example, if we look at zinc, okay, the reduction of zinc is negative 0.76. So that's unfavorable. Zinc really doesn't want to be reduced. It would rather be zinc ion than zinc metal. So if we reverse the reaction, okay, and look at the oxidation of zinc, then it becomes positive 0.76 volts. So we could say that zinc has a much greater tendency to be oxidized than does silver. Okay, because this oxidation is positive, this oxidation is negative. So if we look at a listing of some standard cell potentials here, basically from positive to negative, right? So these are ranked from positive to negative. So at the top, we have potentials that are favorable as reductions. And as we go down, these become more negative, so they're not favorable as reductions, but they would be favorable as oxidation. So if we reversed all these reactions and wrote them, as oxidations, then these numbers would be positive. Okay, so the things at the top have a strong tendency to be reduced, and the things at the bottom have a tendency to be oxidized. So this is moving down. This is decreasing tendency to be reduced. And if we reversed all the reactions and made oxidations, then they would decrease going bottom to the top. So things that have a strong tendency to be reduced, on the way it's tabulated here, things that have a strong tendency to be reduced are at the top. So this is decreasing tendency to be reduced. So if you're thinking for a minute that this is sounding a little bit familiar, it should be, because you saw something very much like this in Chemistry 1. We didn't call it a table of reduction potentials. What we called it was the activity series, where you were talking about single replacement reactions and whether one element can displace another. And you probably had a listing of elements where one element can displace another if it's above or below it in the series. It's the same thing. What you were doing there was ranking elements by their tendency to be oxidized or reduced, and we're doing the same thing here. So the potential for a reaction is the sum of the potentials of the half reactions. Okay, remember what I said about a half reaction can't occur by itself. There's always a pair. You can't have an oxidation without a reduction, because reduction is consuming electrons. Where are those electrons coming from? They're coming from an oxidation. Okay, so potential oxidation and reduction always occur together, and the potential for the reaction is the sum of the potentials of the half reactions. Okay, and so, like was the case for the individual half reactions, the reaction only occurs spontaneously if the cell potential is positive. Okay, so let's look at this example. We want to look at the reaction between silver metal and zinc ion in solution to give us silver ion and zinc solid. So in other words, something like this. All right, so we have a solution that has some zinc ion, and what we want to do is put some wire strip made out of silver. Will we get a reaction? Okay, so we're going to calculate the potential for this reaction. So you ought to be able to see that zinc is being reduced. We have zinc 2 here, we have zinc 2 here, and zinc here. So zinc's being reduced. So the zinc 2 is picking up 2 electrons and becoming zinc solid. Right, so we look at our table of potentials, and where we find zinc. Alright, so zinc 2 to zinc is negative 0.76 volts. Alright. Now, silver, though, is being oxidized. Silver metal is becoming silver ion. Alright. So if we find silver ion picking up an electron and becoming silver is positive 0.80, but that's a reduction. Right? This is one more time, this is a table of reductions. So the silver so the oxidation potential is the negative of that number, so negative 0.80, right? So I multiplied the silver reaction by 2 to make the electrons balance. So basically, so the electrons will cancel and these two reactions will add to this reaction. But you do not, I did not, and you do not multiply the potential by 2. It's minus 0.80 volts, whether you multiply it by 2 or 3 to whatever equation you're trying to balance. You do not multiply the potential by the balancing coefficient. It stays as 0.80 volts. So add the reactions together, add the potentials together, negative 0.76 and negative 0.80 adds to minus 1.56 volts. Alright, so this is a negative cell potential, obviously, so this reaction would not occur spontaneously. So a piece of silver and a zinc containing solution, nothing's going to happen, no reaction. Alright, so the last thing I want to talk about here for this video is the standard hydrogen electrode. Alright, now remember I've said this a couple of times now, a single half reaction can occur. Oxidation and reduction always occur in pairs. But then the problem is, how do you measure the potential for a half reaction? A half reaction can only happen in pair with another reaction, and then the potential becomes the sum of the two. So how did we figure out these values for individual half reactions? Okay, so how are the voltages for individual half reactions determined? You have to have a reference. You have to have a reference electrode. Okay, and in this case, that is the standard hydrogen electrode. Okay, so what is the standard hydrogen electrode? It consists of gaseous hydrogen at a pressure of 1 atmosphere, bubbled over a platinum electrode in a 1 molar solution of hydrogen ion. Right? That's standard conditions. 1 atmosphere of pressure on the hydrogen gas, 1 molar concentration of hydrogen ion. And this is defined, it's defined to have a potential of 0 volts. Okay? So this is no different than saying this volume is 1 liter or this length is 1 meter. Okay, this is just creating a standard potential, so we're defining this to be 0. And note that it doesn't matter which way the hydrogen electrode is going, because positive 0 is the same thing as negative 0. Alright, so whether we're going H2 to H plus or H plus to H2, either way, whether it's an oxidation or reduction, it's 0. Okay, So for example then, if we pair the standard hydrogen electrode with the reduction of zinc and we measure the potential to be negative 0.76 volts, well, because this is defined to be 0, we know this to be negative 0.76 volts. So the sum for the potentials is negative 0.76 plus 0 is negative 0.76. In other words, because this one is 0, the potential for the overall reaction is the potential for the reduction of the zinc, right? And that's the standard hydrogen electrode. And we'll stop for this video.